All right. So I'm ready to start tonight's lecture. We got about another minute or so before we start.
Yeah, but I want to throw it on my television so you can hear.
Yep, I can
I
hear
normally
you.
use my headset. Like the
Yo,
monitor
Joshua, your
audio
mic's
is
on, buddy.
awful. Okay.
Oh, my mic is certainly on.
Oh, yeah, I guess I could use those. I haven't. Um, yeah, on your phone, or you can just ask him. Oops. I thought you got kind of upset at us because people were signing on with different names instead of their class names. Is that true?
I think everybody is supposed to sign in using their class name. People who do not got that, or those people are already kicked. I mean, if you want to abbreviate your last name to a single letter, that's fine too. All right. Well, it is 5:30. I'm going to get started here. You guys are going to get a longer lab today at the end of the lecture, and this one has to do with subroutines. So we'll go ahead and review what we talked about last time just a little bit, and I'm going to use a sample program to illustrate it. So let's go ahead and take a look at a sample program. Okay, and this time we'll start with something that's a little bit more interesting. Okay, which is one way to describe it, I suppose. So we're going to look into something that looks like this. Okay, we'll say your function f has a okay unsigned. Okay, so it returns an unsigned type, which is a scalar. So that should remind you, which register we have to use to return a scalar. And this is the subroutine itself. It has one single parameter, and we'll just call it n. And right now you should probably be thinking about, oh, okay, so that parameter is going to be on the stack. Okay, and then we will go ahead and fill in what is inside this particular subroutine. So depending on how comfortable people are with the ternary expression, I can use a single ternary expression for this one, or I can use a conditional statement. So are there any preferences in the class? You can either type your preferences or you can just speak on the phone. It's okay. Somebody wants to see the ternary operator. All right. And a few other people are okay. We got two people saying ternary, ternary. Okay. So we'll go ahead and start with the ternary operator. Okay. So we say return, and we basically need to see whether n is 0 or not. So we say when n is 0, okay, we return the value of 1. Otherwise, we return a recursive call. Okay, so we're going to say we'll return 2 times f of n minus 1. And that's the ternary operator or ternary expression of what I want to express. So just as a quick reminder, this is the condition of the ternary expression. It evaluates to either 0, which is false, or true when it is non-zero. This is the value for the entire ternary expression if and only if the expression is true. This is the expression, or this is the value to return, or this is the value of the entire expression if and only if the condition is false. So this describes function f. So if you think about what function f does, okay, the first thing is we know that it's recursive because f is calling f itself. But the second thing we also notice is when n is 0, it simply returns a value of 1. For anything else, it returns 2 of whatever f of n minus 1 is. So effectively, if you try to implement this particular subroutine in C, and actually observe what it returns, it's basically 2 to the power of n. That's all it's going to compute. All right. So now we go to main, and this time we're going to have a local variable. So we have a local variable called unsigned x, and in the program we say x equals to f of let's just f of 3, okay? Because that would give us 4 levels of calls already, because n equals to 3, 2, 1, and then 0. So we'll have 4 levels of calls in this case, and that's all we're going to do. Okay, so this program is not going to do a whole lot, except we compute 2 to the power of 3, which we know is going to be 8, put it into the local variable x, and that concludes the execution of this program. So this program serves a few purposes. The first one is a quick review of how we push parameters on the stack, how we call a subroutine, how do we return from a subroutine to the caller. But in this case, it also serves the purpose of what about local variables? What do we do about local variables like that? Okay, and also one more extra purpose, which is kind of like, well, it's not really something that deserves a lot of attention, is how do we deal with recursion? Okay, so recursion really has nothing to do with how we call and how we return. Whether f is calling another subroutine or itself, it doesn't change the mechanism. It doesn't change how we push the parameter on the stack. It doesn't change how we return the value, through register A. Nothing changes, whether it is recursive or not. So as long as I'm not requesting you guys to write a recursive subroutine, um, like in terms of pseudocode and C code, translating a recursive subroutine from C to assembly has is basically the same as translating a non-recursive subroutine into assembly. Okay, so I'm not going to run the program in C, okay, because that's not going to be very exciting, and instead I'm just going to translate this program into assembly code. Okay. So instead of doing everything in line, I'm going to start a new window on the side. So this way, we have a separate window to represent the assembly code. So in the assembly code, the first thing is no op, okay, to get the command line mode of logit sim to work, okay. And then the second thing is a JMPI to main, because we sort of want to maintain the ordering of the subroutines and main, okay, which is not necessary because we can totally reorder and have main defined before F, that would work as well. So now we can go ahead and implement the subroutine F. So when we implement the subroutine F, the first thing we want to do is to kind of keep in mind what is on the stack at this point. Okay, so the stack at this point is going to have 2 items for sure, because based on the agreement between the caller and the callee, there are 2 items here. Because the caller says, okay, subroutine, I'm going to give you 2 items here. One is the parameter, and the other one is the return address. So I'm going to say return address is here. The square bracket, once again, just like in the previous lecture, is really just denoting that the stack pointer is pointing at this particular item on the stack. And then at a higher address, which means it's pushed a little bit earlier, is the parameter n on the stack. So we know at this point the stack should have at least these 2 items. Now, can the stack have more items at the higher addresses over here? Absolutely. But I really should not care about those items because they do not relate to me as a subroutine being called. So now we go into the subroutine here. And the first thing I would do, this is just me doing it. When you guys implement the subroutine, you don't have to do it this way, but I think it's a good idea to do it this way. Is I have a return address that is defined to be 0, and then we have f here defined to be 1. So once again, just like in the previous lecture, f is not the actual excuse me, it's not f, it's supposed to be n. So n, once again, is not the actual parameter. it is defined to be 1 because the parameter is 1 byte away from where the stack pointer is pointing to. That's why it's defined to be 1. I do want to use a label definition because this way I can just refer to the displacement using the name of the parameter so that I do not need to. Yes, so Nick is correct. That should be n, and I just fixed it. I wasn't keeping an eye on the Discord channel. I suppose I should be doing that. I have to move the window a little bit so it's actually within my. I can actually see activities in that window. Okay, so once this is all done, then what we need to do is to look at the return statement. The first thing we need to do is to retrieve the value of parameter n. To get to the value of parameter n, the first thing we need to do is to look into the address of n. Okay, so the way that we talked about this the other day or on Tuesday is we do LDI, and at this point register A, B, and C can all be used. Register A has no special meaning at this point of execution, so I can always just use register A. I put n into A, which is the same thing as a LDI A1 because n is just a symbolic name defined to be 1. And then we do an add AD. Okay, so this is a trick because if I want to comment on what is in a particular register, A has 1 at this point, okay, and it's a double equal because that just means A does equal to 1 at this point. And now A equals to 1 plus whatever the stack pointer has, and what is 1 byte away from where the stack pointer is pointing to? It's parameter n on the stack. So now A is not n, but the address of n. Okay, so it's really important to differentiate between the value of a parameter or a local variable from its address. So you have to get to the address first before you can get to the value. Okay, but we are not really exactly interested in the address itself. It's just a way to get to uh, the parameter, and then we load the reference, okay, which is a LD instruction. So we do a LDAA, so that A is now whatever it is pointing to, which is whatever, which is dereferencing the address of n. So when you dereference the address of something, that's just the value of something. So in this case, now we get to the value of n. So this particular sequence of instructions, LDI with the offset, add the stack pointer to that offset, and then dereference the address. It's a pretty common sequence of instructions from here on. So you would see this kind of over and over again. Do we have any questions? I hear a mic wrestling. Nope. Okay. All right. So if there are no questions, we continue our discussion. All right. So I think Lee has the mic on and we can hear some of the stuff going on in the background. So Han, you might want to consider muting the mic until you're ready to talk. Okay.
Professor, I have a question.
Yes.
Uh, the advantage of using n and the return address definitions here is it just means that we don't need to change this for if we want to copy it into a new function, right?
It means if we need to introduce another parameter, we can just refer to the name instead of having to keep in mind where exactly is it on the stack. So is that working or not?
I think that makes sense. I just
Can you
still
elaborate on that?
What was that?
I'm just saying I'm still not 100% sure on why what why that is easier than just saying um, LDIA1
Oh,
add
be,
AD LDA.
because your function can be pretty long and you can have a lot of different parameters. So when you have, like, let's say 3 or 4 parameters, it becomes kind of a hassle to have to remember which one is where. So in this case, you can see that if I look at the code in C, which refers to the name n, I can also just refer to the name n instead of having to try to remember where n is when I'm trying to compile the rest of the program or the rest of the subroutine.
Oh, I see. Now I'm getting it. Thank you,
Yep.
Professor.
Okay, you're welcome. All right. So now that we have register A having the value of parameter n, we can now compare it to 0. But we know a trick so that we don't have to actually load 0 into another register and do an actual compare, because we have an instruction, I think it's AND, that is still doing what AND is supposed to do. Okay, OR is hijacked. Okay, this is from an early homework assignment. The opcode of OR with of a register with itself is already hijacked to do, I cannot remember, it's increment or decrement, one or the other. But AND is not hijacked. In other words, if I say AND AA, what this is going to do is to say, okay, this is a single equal sign because it's an assignment operation. It changes, quote unquote, changes A, register A. So the A is the bitwise AND of A itself. Okay, let me put parentheses around this. And we know that anything and itself is just itself, okay? Because 1 and 1 is 1, 0 and 0 is 0. So A and A is just going to be A.
Giờ này nó mới ăn một đống cái gì cá của anh và giờ anh cho nó ăn nữa rồi hả?
Okay, so Han, you might want to turn off your mic. Han?
Tại người ta cho nó bớt ăn lại, cho nó ăn ha. Một ngày cho nó ăn 2 cữ thôi mà anh quất cho nó quá trời luôn à. Sao mà nó ốm
Han,
nổi?
you might want to turn off your mic.
You might need to mute him for the whole channel.
Yeah.
He's not
I
hearing
don't
what you're saying.
I don't know whether I can do that. Can I do it? Okay, I can do a mute here. Let me see what I'm actually muting. Oh, okay, that seems to work. Is that good so far? I think I just muted the other person. Mute only works for the person, but I can actually mute everybody.
No, you can mute somebody and then you can't hear them. The rest of us still can.
Oh, okay.
So we all have to go and
right click. Yeah, so go ahead and right click on that person and then click on mute. So I'm just gonna type it here. Okay. There we go. So are we ready to move on? All right. So I'm guessing we are good to go. Okay, thank you, Nick. All right. So getting back to this discussion here, and AA really doesn't change A. I mean, A is unaffected by and AA. But, when we look at the ALU, any type of operation will go through the checking of two flags. The Z flag and the S flags are always changed by anything that goes through the ALU, except for increment and decrement. Those are a little bit special. Yes, it doesn't quite reset the flags, but the flag is going to reflect the result of the AND operation. Okay? And as a result, the Z flag is affected, and so is the sign flag, but in this case we are not. The Z flag is this 0. That is correct. So the Z flag is a 1 if and only if the result of an operation is a 0. So in this case, the Z flag is going to be set if and only if A and A, gives us a 0, which means A itself has to be 0 in that case. Okay, so let me just kind of comment a little bit more here. So as a result of this operation, Z is a 0 if and only if A is a 0. Z is a 1, sorry. Z is a 1, the Z flag is a 1 if and only if A is a 0. Oh, okay, thank you. All right. So I can go ahead and unmute. Okay, so that way if Han has a question, he or she can let us know. Okay. Very good. Cool. All right. So next thing we need to do is, well, now that the z flag is changed potentially by the AND operation, we better act on it. Okay, so that means we have to use the JZI. JSI is not going to help us with anything because we need to know whether the entire register is a 0 or not just the most significant bit. So we have to do a JZI, but when we label the when we come up with a label for this JZI, we kind of have to think about, okay, where are we branching to? We are actually branching to the then portion of this ternary expression. So we might want to label, make a label that is a little bit makes a little bit more sense. Okay, so I'm just going to use f underscore then, which means it is the then of f. Okay, and Nick is typing. Okay, f then is just going to yes. So now we just go to so as a usual practice, when I have a JZI or some kind of conditional branch, right after the JZI, I'm gonna write down what does it mean if I get here. So when I get here, it simply means that n is greater than 0 or not equal to 0. So technically, not equal to 0 is really the same thing as greater than 0 because n is unsigned. If n is unsigned, it cannot be negative. So if it is not if it cannot be negative and yet it is not 0, that means it is greater than 0. So in this particular case, n does not equal to 0 and n is greater than 0 are actually the same thing because n is unsigned. Okay, the reason why I like to do this comment is so that when I go back to read this code, I have an idea of what does it mean if I do not take that branch. Okay, so when we do take this branch, we also want to label that n does equal to 0 in this case. All right, so we have a choice now. Okay, because we can go ahead and define the label here. And so we can either choose to do something here, which is saying, okay, we are handling the else part of the ternary expression, or we can go ahead and go here to deal with the then branch of the ternary expression. So as Nick said, this is pretty easy. We'll take the easy pieces off first. So we specify LDI A1, okay, because we specify a return value of 1. Okay. And depending on how we structure the code, we can just kind of continue here. So we just say, f return code is all the way here, and then we put the else branch over here. In other words, when you look at the assembly code, the ordering is a little bit different compared to the C code because we put the else code, quote unquote, ahead of the then code. But this way you also save, an additional instruction because otherwise you need a JMPI to go to the else case, which also means you need another JMPI here to get around the else case. So instead of wasting 2 additional JMPI instructions, we can just kind of do it this way. This, not having unnecessary branch instructions is kind of a big deal when it comes to trying to get a processor to execute instructions as fast as possible. Because when we change the direction of execution, what that usually do, or what it can end up happening, is it can cause a pipeline to be abandoned because the predictive behavior of a processor of, oh, I bet you want to execute this instruction that's after the current instruction, and it will try to pre-execute at least a certain part of it, because it's actually a pipeline. So when you have a branch instruction, especially a conditional branch instruction, it's going to have to abandon that. The other part that has to do with branching and efficiency has to do with prefetching stuff. When you buy a DDR type memory, the reason why it is quote unquote faster compared to non-DDR memory has to do with DDR memory, it works in conjunction with cache. So whenever you need to access a new location because it's not in the cache, it will pre-read a bunch of locations, not just the location that you want right away, but it will pre-read like 64 or 128 locations into the cache. So when you have a branch, that means, oh, guess what? Those extra bytes that we read a little bit earlier, most of those are not going to be useful anymore. Now, obviously, that has to do with how far your branch is, okay? But in general, branches can basically cause the execution to go out of what is already cached or what is already read ahead. So it's really a nice thing not to have to branch. So that's why, I'm going to minimize branching over here and then put the else expression over here. Okay, so the else expression now has to jump over the then expression, but that is unavoidable. There's just no way to get around this one. There are some tricks we can do so that we can avoid unnecessary branches even more, but I'm not going to do it over here because I think it might just be causing more confusion. So I'm not going to talk about that at this point. Maybe later on we can talk about that technique. Alright, so the else expression is we have to figure out what is f of n minus 1 and then multiply that by 2. Okay, so the first thing we need to do is to find out, okay, we have to call f again, and this time, we have to figure out what is n minus 1. So how do we do that? Well, we are going to call f the same way as main is going to call f. So the mechanism of calling a subroutine does not change just because it is recursive. So right now we have to say, okay, first thing we need to do is to push n minus 1 on the stack. Then we have to push the return address on the stack. Then we do an unconditional branch to the subroutine we're calling. When this is all done, we have to clean up the argument and make use of the return value. Okay, so all of this stuff here really doesn't change whether it's recursive or not. Okay, so we'll start with the first one. How do we push n minus 1 on the stack? Oh, we have to get to n first. But wait, n is already in register A, so we don't have to actually recalculate it. So we might want to make a note here and say that A is register A already has the value of n. How handy, right? I mean, because all we have to do is now we can decrement register A. So now A equals to n minus 1. So note that we are not actually changing parameter n. We're only getting a copy of of parameter n and decrementing that copy of parameter n. So n is still sitting on the stack intact at this point. Okay. Now we need to push it. Yeah, it's sort of like a local variable. So now we decrement d to allocate the space, and then we do stda, so that we are now pushing n minus 1 on the stack. We need to push the return address now, decrement d, and then we do the trick that we did before, which is ldia with .5 plus, which is the address of 5 bytes from the beginning of this LDI instruction. We talked about this in the previous lecture. And then we have to do the store. Don't forget store, because otherwise you're doing everything except it's not really pushed. Okay, so we push the return address on the stack, and now we can just continue execution in the subroutine, which turns out to be the same subroutine that I'm in at this point. But it doesn't make any difference. Okay, this is how we call a subroutine: push all the arguments, push the return address, and then do an unconditional branch to the beginning of the subroutine. Okay, so when we come back, it's going to be over here. The first thing we do is we clean up the stack because the argument is still sitting on the stack. So what we do is we just increment d to clean up the argument, which is sitting on the stack. So now that we have cleaned up everything, we can now make use of the return value, which is in register A. So register A already has f of n minus 1, but we want twice of that. Okay, and this processor has no multiplication capability. So how do we do a multiplication by 2? Do we need to clean up the return address? The answer is no, because the called subroutine is going to clean it up. Okay, and Alex is also correct that we can just do the doubling by adding something to itself. Okay, so we're going to say add AA. So A is now twice of what it used to be. So A is now twice of f of n minus 1, which is exactly what we want. Cool. And we can then go around the then branch and go to the return label. So now we just do the usual stuff, okay? Just be careful not to use register A in the process because register A already has the return value. So we just do a LD BD, and so now B is the return address, and then we increment D to deallocate it from the stack, and then a JMPB to go back to the caller. Okay. So now the question that some of you might have is, but what if the caller is f itself? Because f is recursive. It's recursively calling itself. Well, my answer is very simple. Why do I care? Why would that be any more special, compared to returning to another subroutine? It is not different, exactly. So Nick is right that it is not any different. Okay, so now we got f done. Let's go ahead and look into main and see what we need to do with main. Return address is up at the increment D earlier if we recursively called. Not quite sure what that means. Where we clean up the argument. Yes. So after we clean up the argument, in other words, right after this increment instruction, register D will once again point to the return address. That is correct. Okay.
That's not what I'm saying. I'm saying when we're calling recursively, the return address that this function is going to return to is up at where we clean up the argument from this function.
It returns to that location.
Yeah, that's what I was saying.
So when after the call, it returns to this instruction. So this is the
that's what I was saying. That's what I was saying.
Okay. Okay. Cool. But I want to make sure the class also understands, what you meant. So what you meant is this is the last instruction before we continue execution in the next invocation of f. But when that invocation of f is done, this is where we get back to into the current, this particular invocation of f. So that is correct. All right, so now we just have to implement main. So what are we going to do with main? Well, actually, main has a local variable. So what are we going to do with a local variable? So now, once again, it is important to get a picture of what the stack should look like. Okay. So if main is any other subroutine, okay, then it's going to have its return address that is pushed by main's caller. Now, yes, your main is not really called, but I'm just pretending main is actually a subroutine. So now, isn't that local variable the return value of a subroutine? Not yet. Not yet. Well, the first thing we need to do is to allocate. Okay. So as it turns out, local variables are on the other side of a return address. So parameters relative to a invocation of a subroutine, parameters are on the positive side of the return address. And as a result, local variables, which can only be allocated by the called subroutine, are on the negative side of the return address. They are allocated after the subroutine gets control. Okay, so in order to do this, now we have to say, okay, if the stack is going to look like this, then x is going to be defined to be 0, because by the time we are done allocating the stack space for x, x is now at the lowest part of the stack, which means the stack pointer is now going to be pointing at x as a local variable, and if main had a return address, it would have been 1 byte after x. Now, main is special because main does not have a caller, so it really does not have a return address on the stack, so we just kind of cross this out. But it doesn't negate the fact that we have to allocate, a particular byte for x. Okay, so we're going to have to do a decrement d to allocate a byte on the stack, and now x actually has a space on the stack. The stack pointer is now pointing to the local variable x. Okay, so now we are done. variables. Okay, well, we only got one, so grammatically we only got one local variable. All right, so now we can actually proceed with the rest of main. So the first thing in main, in terms of what we need to do is to call f with a parameter of 3. So we know how to do that because we just LDI a with the actual value of 3, decrement d, store to the stack pointer a, which has a value of 3. That's how we push 3 on the stack. And then we decrement d again. This time we LDI a with the return address, which is .5 plus. And then we store to where the stack pointer points to a, but this time a has the return address, so we're just pushing the return address. Now we can continue execution in the subroutine, which is f, and when it returns, it's going to come back to the location where the blinky cursor is. So at this point I can say, well, the first thing we need to do is to increment d, because the argument that we pushed earlier, which is due to these 3 instructions, that is still on the stack by the time we get to the increment d instruction, and that is really not useful anymore. The subroutine is already done. Why do we want to keep the argument on the stack? So we do an increment d to get rid of that. Then what about the return address? Okay, the return address is pushed by these 3 instructions. Isn't that also on the stack? The answer is no, it is not on the stack anymore, because it is the responsibility of the called subroutine to clean up the return address. Now you might want to say, but that's asymmetric, because for certain things, the caller allocates and the caller deallocates. And for this one thing called the return address, the caller allocates, but then the subroutine deallocates. That doesn't seem to be symmetric or consistent with the other stuff. Well, you can look at it that way. But the other way to look at this is the call is typically implemented as an instruction, as a single instruction in most Cisp processors, and then the return is implemented as a single instruction as well. So it makes more sense in that case that the return would also clean up after the return address. But in the RISC processor, where we are actually free to break up when we use the return address and when we free up, yeah, you can kind of say that it seems more symmetric if the caller is responsible to deallocate the return address. But we're going to stay consistent with the convention of most compilers, so that it is the called subroutine's responsibility to clean up after the return address. Okay. So now the stack is all good again. Okay, the stack pointer should be pointing back to x at this point, and we need to store the value of f of 3 into x. So what are we gonna do? Now we can do a simple thing. Okay, this is as simple as it gets. Okay, in order to say that okay, x is not now getting the return value of f of 3. Yes, we can do that. Okay, but I'm not going to do it. I'll do it in a very kind of convoluted way, or overly convoluted way. I'm going to do LDI B. Now be careful not to use A, because right now A has the return value of f of 3. So it's important to make sure that we do not use register A until we get to actually utilize register A. Okay? Until after we actually use register A. So we have to use register B for this case, in this case, and we load it with X, and then we say add BD. Okay, so once again, what is this saying? This is saying, B is 0. This is now saying B is the address of X. And what do we want to do with X again? We want to store to local variable X. So that means we're going to have to do a store now to indirect to B, and the return value is already in register A. So this is what we're going to do. Okay, this is actually going to do store f of 3 into local variable X. And I know some people are going to say, but that means we have 2 extra instructions that are totally useless, because all we end up doing is saying that B is really the same thing as D, and then we dereference register B. Why don't we just dereference register D to begin with? The answer is if I want to make this program bigger, longer, and more complicated, I might define local variables before or after x, in which case x is no longer at offset 0, which also means that I cannot just assume that register x, parameter x is where the stack point is pointing to. But if I do it this way, yes, when x is the only local variable, it seems to be a waste of instructions. But as I make the subroutine, make main more and more complicated, I don't have to do a single thing to come back and say, well, did I do some shortcut that I have to undo later on? Okay, so this is really just for the future, so that we don't have to worry about things when we want to have more and more local variables. So now we can move on, and we can quote unquote just do a halt here, okay? Because we are now at the end of the subroutine. But we still got one extra thing on the stack that is not useful anymore. That turns out to be local variable x. Because as a local variable, the subroutine that contains the local variable is responsible to allocate it, but it's also responsible to deallocate it. And as a result, over here, we really need to do this increment d to deallocate local variable x. So I'm just going to pause a little bit so that people have a chance to read main and see if there are any questions about main. All right, no questions. Okay, so what we'll do is now we'll go to the assembler. Okay, with Control A, Control C, and then we switch to the assembler, because we want to run this program and see what it looks like when these instructions execute. Okay, so we go here, and the previous time I I placed the program code to a place that's much later, so I'm just gonna have to make sure that I erase those locations. Alright, so we kind of go back and make sure that things look good. No, these are not supposed to be here. Okay, so we got the halt as our last instruction, and when we go to RAM file, we make sure that the first line says v2.0 raw instead of there are errors. So we are good to download this into a RAM file. So we'll download it to a comma separated value file, and then we'll save it into the temp folder, and I'll call exp2 because it's really 2 to the power of n. Okay, save it, and now we can look for a command line interface. There we go. This looks good. Okay, I'm gonna put it in view here. So I'm just doing I just type an up arrow because this is really kind of close to what we need to do, except the program is not 7 anymore. This time it's exp2. Everything else will keep exactly the same. So we press the enter key, and it's all done. So one thing that I really should point out is if you press the enter key and it takes an excessive amount of time and it's still not done, chances are you might have an endless recursion or an endless loop of some kind, so that the program does not exit. Okay, so in that case, it does get a little bit more difficult to debug the program, because you would have a long trace after this, and then you have to look into that trace and find out where that loop is. But in this case, the program did terminate. I have a log file, which is the result of redirecting the output of Logisim in command line mode to a file called log.tsv. So, excuse me. So now we get to the trace analyzer, and make sure sheet 1 is the tab that is active. And then we go to file. There we go. And we import log.tsv, just right here. Then we click open. Click import data. And then wait a little bit. And I can switch the tab to the analysis tab because when it's done, this is the tab that we need to look at. But right now there's something here, but not the entire thing yet. There we go. Okay. Almost there. There we go. Alright, so the first thing we want to do is to figure out, did we actually get to the halt instruction? And where is that halt instruction? So we go back to the assembler, go to the assemble view, and then we scroll down until we find that halt instruction. The halt instruction is on line 58, and the location of the halt instruction, if I scroll let me turn off this vertical tree tab here. So the location of the halt instruction is 2D. So one thing we can really quickly do is to locate 2D in column A. So we go to, I think we can do a Control F to start searching, maybe. Oh, come on. Okay, we'll do it one more time for waiting, and then I'll stop it. There we go. So we want to search for 2D and do not match case because I think the trace analyzer uses all uppercase. So 2D, and then we just find it, and there we go. Okay, this is 2D, which is the last instruction to execute because there's nothing after this in the trace. We can also see that right before we get to the halt instruction, the stack pointer is balanced again. Okay, so when I use the word balanced, it means whatever stack pointer we start off with is whatever stack pointer we end up with. Okay, so we are not storing any additional items on the stack. So when we go back just a few cells, we can see that location FF is now storing the value of 08. Well, that's good because that tells me that X, which is the local variable of main, is storing a value of 8, which is really 2 to the power of 3. So the program does work, okay? But the more important part for you guys to go over, is to go take a look at how the stack is utilized. Now, how can we identify and isolate stack-related operations? You have to go to register change and look for things that changes register D. Okay, so when you see D equals something, that's a change to register D from what it was before. I believe this one is an increment. Okay, this is incrementing D from FE because we are at the end of a subroutine, and we have just utilized the return address, so we are incrementing D from FE so that register D points to the local variable X again because we just made use of the return address. So if you go back up a little bit earlier, you can see how we make use of the return address. This is the return address. Okay, so we store the return address into register B. This is the LDBD instruction at the end of F, and this is the increment right after that. Okay, So if you say, well, but you can claim anything you want, how do we know that really is the case? Easy. You look at the address. Okay, this is at address 19 in hexadecimal. This is address 1A in hexadecimal. So I claim that the 19 location has a LDBD instruction, which is at the end of F. The 1A location has an increment D instruction, which is right after the LD BD instruction. So to double check that, we can now go back to the assembler and we go to those two locations. And of course, I completely forgot about the locations already. So it's 19 and 1A. So we scroll a little bit until we find 19, which is here. Okay. So that turns out to be really the LDBD instruction. And then the next one, which is 1A, really is the increment D instruction. So by following the trace analyzer, you can actually look at the execution of a program not only from top down or going in the forward direction, but you can actually back up as well. Okay, you can actually execute a program somewhat in reverse by scrolling up like this. Okay. So are there any questions about how to make use of the trace analyzer, especially in the context of the program that we are talking about? Let me go back to the C version of this program, because I think that's a good starting point for any further discussion. So are there any questions about this program? How it makes use of the stack, how we call, how we return, how do we push an argument on the stack, how do we access a parameter in the called subroutine, and how do we allocate a local variable in the subroutine? Are there any questions about this? No questions so far. Okay, there's a question. Okay, let me go back to Discord. Alright, so there are two questions. The first one is from Joshua. So is that why we always exit main with return 0? It's returning back to the start of the stack. No, the return 0 is completely decorative as far as the program is concerned. So return 0 in an actual C program is returning an exit code of 0 to the operating system. So the operating system can use the return code of a program to determine whether the program terminated normally or not. A return code of 0 is normal. Anything other than a 0 is not normal. But in this case, the toy processor has no operating system to return to, so the return code is really useless as far as um, that particular purpose is concerned. So that 0 has nothing to do with D being 0. D is 0 only because that's where we start the stack, or that's the last location of the stack. Now, if you want to allocate certain spaces close to the end of RAM, and you say, okay, the stack needs to start lower, you can do a LDID with a different value to start the stack. So it is just coincidental that the return 0 has a 0, and the stack pointer, which is registered D, also ends up with a 0 at the same time. And then Garrett's, so not so much the question, but a request is, can I put the text file on Canvas so we can look at it later? The answer is yes. Okay, so in fact, let me think about how to do this. I can combine the two into one, which means the first part is going to be C code, the second part is going to be assembly code. So if you want to get it to work, you're going to have to like comment out one part of it. Okay, but I can combine the two into one single file, and I'll do the ultimate lazy thing, which is copying this and putting it into, okay, where is, okay, that's your lab tonight, which is function calls. But I'll put it over at a location that's easy for you guys to find because it's related to this lab. Okay, so just do a plus. and I'll make it a web page by itself. It's going to be a new page. Oh, failed to create new item because I didn't give it a name. Okay, so we'll call this a name. We'll call it exp2 sample program. Add item. And of course, Canvas has to make this a multi-step process. It could have just asked me, oh, what is the actual content of the document that you just created? No, I have to do it. Click on it and then edit it in order to paste that in. Alright, so here's where I'm going to paste it, and I think I can use TT or the text, the program text tab, but it doesn't have that. It's okay. I'll get into HTML editor. There we go. So we'll do a pre-formatted. Okay, we'll do the begin and the end tab, and then paste the actual code in between, and that should work. Save and publish. There we go. Alright, so would that work? Okay, no comments. Oh, okay, gotcha. You're welcome. Alright, so are there any questions whatsoever? Because this is a pretty important program to understand, because it excuse me, because it repeats certain things that we have already talked about, but at the same time it also introduces something that's new, which is recursion and local variables. So if you have any questions, now is a good time to ask. No questions. All right, well, if there are no questions, I will give you, let me look at the time. We got about another 25 minutes. I'll give you another sample program. Okay, so you have more programs to look at in order to understand how to call a subroutine and how to make it work. Okay. All right. So the next program I want to show you is string length. Okay, how do you find the length of a string? Okay, that's usually a pretty easy thing to do. Okay, so you have string length, and you have to give it a pointer to a character. So in this case, in regular C, you basically say const char, and then whatever the string is that you want to find the length of, and then in here, you define the subroutine. Okay, so there are obvious ways to implement string length, which is to use a loop. Okay, so here's a question. Do tail and no tail recursion work differently in assembly? So that's a very, very good question. Okay, so if for people who do not understand what is a tail recursion, it means the recursive call is at the very end of a subroutine. So in the case of the program that we just looked at, it's sort of like that too. Okay, in fact, anything that has a single point of recursion can be seen as a tail recursion. So in this case, because we are doing a straight compiling from C code into assembly code, so we do not have any special consideration whether it is a tail recursion or not. What Joshua is mentioning, why tail recursion is special, is because if for certain programming languages, if the language recognizes that it is a tail recursion, which means the recursive call is at the very end of a subroutine when it calls itself, then it's not actually going to push additional return addresses on the stack. It becomes basically like a loop, like a normal loop. It gets optimized out. Exactly, Ramsey is also correct that it will optimize out the additional push and the additional pop of return addresses. But C doesn't do that. Okay, when you implement a subroutine in C that has a tail recursion, the compiler typically, as far as I know, no C compiler would optimize out that actual call. So since in this class we only translate C code into assembly code. So we will all just follow the C code standard, which means we do not have any special consideration when the recursive call is at the very end. So I hope that answers the question for Joshua, and thank you for and I'm thanking Ramsey for pointing out that it is just optimized. So are we good so far? Or okay, looks like we're good. Okay, so we're gonna move forward and implement string length. So I'm gonna do it in the same style as the other one. We'll do it recursively and using only one single return statement using a ternary expression. You guys can start to see how much I like recursion and how much I like ternary expressions. So in this case, we'll take a look at whatever string is pointing to, str is pointing to, and if it is a non-zero, then we'll go ahead and specify some kind of return value. Otherwise, we return another value, question mark and colon. I got it all reversed a little bit earlier, but that's okay. All right, so whatever the blinky cursor is at this point is to specify the then expression, which means if str is pointing to something that is not null, which is the terminating character of a string, then we're going to do this. Okay. So what we'll do is to say, hey, I know this string has at least one character because whatever str is pointing to is not null. I'm not looking at the end of the string, which means this string has at least one character. So I'm going to say 1 plus, okay? 1 plus what? I really don't know what is in the rest of the string. So I'm going to call somebody else to find out how long the rest of the string is. But whatever that is, the actual string that I'm responsible to find the length of is going to be one more than that. So now we have recursive call to string length again, but str is now str plus 1 because str plus 1 is basically the address of the next character. So if str is pointing to a character that is non-null, which is something that I just checked, then str plus 1 is the address of the next character, which also can be seen as the beginning of the string or the substring that is right after the character that I just looked at. Okay. So now we can also try to handle the case, what if star str is a 0? What if str is pointing to a null terminator? Well, then we just have a string that has a length of 0. This is how we end the recursion. So yes, I understand this is not really the best implementation in terms of efficiency, but in terms of demonstrating how to call, how to return, and how recursion actually works, this is actually pretty good. Okay, so now we have main, and then we'll go ahead and, just like before, have an unsigned x as our local variable, and then we say x is the string length of the literal string of tag. Okay, which has a string length of 3, and then we have a return 0. All right, so this program presents a few interesting questions to answer. Okay, not so much the string thing, but we have a dereference here. So what do we do when we need to dereference a parameter? Okay, that's one question. A more interesting question is, what about literal strings like this? How do we deal with literal strings like that? Okay, that's a second question. So this particular sample program will address both of those questions. All right, so we'll write the code again, starting with no up. And if for people who said, but you forgot to initialize the stack pointer, fine, we'll initialize it here. Then we jmpi to main. Okay, so that's really just the starting of a program, so we can, get get the stack pointer initialized and also start with main, at the beginning. So we'll start with string length. Okay, string length is pretty easy because just like last time, the return address is pointed to by the stack pointer with the parameter str 1 byte after that. Okay, so we'll go ahead and define the labels kind of the same way, except this time we have str instead of n, okay, which is 1 byte after where the stack pointer points to. Okay, so now we can start with the actual implementation of the subroutine. So we use the same technique. Okay, we say LDIA with str, add AD, so that we get to the address of str, and then we do a LDAA, so that A is now finally the value of str. So A is the same as parameter str, but it is not str that we are interested in. We want to get to whatever it points to. Okay, so whatever it points to is something that we want. So we need another LD instruction to do it. But this time I'm going to use a different register, so that B is now whatever it's the dereference of whatever A has, which is the same thing as dereferencing str, like that. So B is what we want to check whether it's 0 or not. Now the question is, well, why don't you just use A again? Well, because I looked forward a little bit and I see that, hey, we need str back. Okay, we don't just want whatever str is pointing to. We actually want str to point it back at some point, perhaps, maybe, sometimes. Okay, so that's why I keep it around in register A, and instead I use register B to store whatever str is pointing to. So in this case, I have to do an AND BB to see if whatever str is pointing to is null or not. JZI to say str length, whatever str is pointing to is null. Okay, so the whatever here is representing is not null. It's not the terminator. Okay, so this time, I'm going to show you a trick to help minimize branching around. Okay, so this is the trick. The trick to minimize branching around is, especially if one of the branches is a really simple one, is to do it first. Okay, so we'll do LDI A with 0. Okay, so basically we are saying, let's assume it is null. Okay, it is an empty string. Okay, so we make an assumption that we're dealing with an empty string, because if it were, okay, it's simple stuff to do. Okay, we just have to reset A with a 0. Now, yes, we do have an instruction between the AND instruction, which is here, which is setting or changing the flag that we want, and where we check the flags. But it's okay, because LDI does not go through the ALU. And as a result, LDI does not change the flags. So it is actually okay to do it this way. Okay, now you can also say that we can put it somewhere else, like put it a little bit earlier. But the earliest you can do it is over here, where the blinking cursor is. So we can put it over here, because if you put it any earlier, then you're going to mess up, how we dereference A to get to B. Okay, so we cannot move it any further earlier than that. Okay, so JCI string length is null. Now really has nothing to do. It really it's just a label to branch around what happens if it is not null. Okay, so now we just have to handle what if it is not null. Okay, if it is not null, we have to push str plus 1 on the stack. But register A still has str, so if we increment register A, then A actually now has str plus 1, which is what we push on the stack. So decrement D, stda. So now we push the argument of str plus 1 on the stack. Then we decrement D again, LDIA, this time with .5 plus. We got a question. Doesn't have a 0. Doesn't A have 0 and not str? Darn it, yes. Okay, Nick is right. Nick caught me. So the optimization, doesn't quite work, because I have one more register I can play with. So we'll play with register C. But then I have to remember to change all references to A to C. But yes, Nick caught the problem. Okay. So that means the more register we have, the better. There we go. All right. So at this point, we have to change this to C, because register A's only purpose is the return value. So for all other things, we have to use register C. All right. So now we have the return address pushed on the stack. Now it's time to pass the control to the subroutine that we are calling, which is str itself. When we get back, we have to increment the stack pointer to deallocate the argument that is now sitting on the stack. Register A now has str of, okay, let me just comment here. Register A has str length of str plus 1. And I'm supposed to return 1 plus that. So I just have to increment A and I'm all done. So when I'm all done, I don't have to branch around the case when string length is null, because that's already handled. Okay, when the string is 0 or when the string is empty, I already have A in register 0 and then continue execution at the label called str length is null. So I just have to fall through. Okay, in this case, after increment A, I don't have to do another branch. I just fall through, and now we can just do the usual return, which is LDBD, increment D, JMPB, and that's string length. Okay, so that addresses one particular question of, what do we do when we need to dereference a parameter? We just use LD again. Okay, that's going to do the dereference. But you have to make sure by the time we do the dereference, whatever register that you're using for dereferencing has the pointer, which is the parameter in this case. So now we get to main. And in main, it's kind of the same deal as last time. The stack pointer should point to the local variable x, which means we have to decrement D to allocate the local variable x. And we also want to define x to be 0 because the stack pointer is pointing right at x. Okay, so there's no offset from where the stack pointer points to get to x. Now we have to say, then how do we push the literal string tag on the stack? That is an interesting question. Okay, so there are several ways to do this. You can define the string after the program or before the program. Just stash it somewhere. Okay, you can do it over here. Okay, so I can basically say this is just a literal string, and I'm going to use 2 double underscore to basically say this is not a normal label. It is an internally used label that does not correspond to a function name, nor a local variable, nor a parameter. Okay, so we'll just call this literal string 1. Okay. Now we can just use the byte directive to specify tag. So the byte directive, all it does is to say allocate 1 byte, and then the content of that byte is whatever we specify here. So now we have to go look up the ASCII code of TAK. Okay, and I am going to look it up using the man page. So man ASCII, and then we just look for T. Okay, so T has an ASCII code of 84 in decimal. So we just put it here, 84. Okay, and then we have lowercase a. Lowercase a should be 97, and then K is, okay, I'm just counting with my fingers here, A, B, C, D, E, F, G, H, I, J, K. So it's 11. So it's 96 plus 11, which is 107. 96 plus 11 is 107. Let me double check. I don't trust my arithmetics. So here's K, which has an ASCII code of 107, so that was good. Okay. So, but don't forget, it also has byte 0 because that's the null terminator. So when you define a string in C, let me switch back to the C code here. When you define a literal string like this in C or C++, the null terminator is there. It's just that you do not see it. Okay. So in assembly code, we have to define it like this because there's no string construct in this particular assembler. Some do and some do not. Okay, so now we have to push the address of that literal string on the stack. So that becomes pretty easy to do. Decrement D LDIA with underscore lit string 1 and store that to where the stack pointer points to. So this is pushing tag on the stack. Okay, it's pushing the literal string tag on the stack. Because when you push a literal, quote unquote, the literal string on the stack, you're not pushing the characters TAK and the null terminator on the stack. You're pushing the address of the string on the stack. Okay, so that is really important, is to recognize that this particular argument over here is specifying the address of the literal string. It is not specifying the actual characters TAK and a null terminator. Then we push the return address. Okay, so by this time we should be pretty comfortable with how to push the return address on the stack. And now we can go ahead and continue execution in the subroutine. When it comes back, we have to deallocate the argument on the stack. So we just do an increment D. And then at this point, we can store register A to local variable X. So just like before, I know this sounds, kind of extra and not needed, but this makes sure that you can just reuse the same sequence of code anywhere you want in the program, no matter which local variable or parameter you're trying to access. And then we do a stb a. So this way, local variable x is actually going to store the value of string length of tag, like so. And this concludes the assignment operation over here. So what is left for us to do is to increment D so that we are now deallocating x as the local variable, and then we can get to the halt instruction. Okay. So are there any questions at this point before I run this code, or assemble this code and then run it in, and then we look at the trace? Are there any questions? Let me make sure that we're still live streaming. Yes, we are. Okay. When I don't get questions for an extended period of time, I get a little worried. Oh, great. Eugene says, what is the deadline to drop the class? You kind of have to look it up on the school's calendar. I don't have the date available to me. Oh, okay. Well, that's one thing about online, especially text chatting, is when I read the words, it's hard to tell whether someone is joking or not. All right. Yes, that is correct. That's why we got emoji. All right, let's go ahead and finish this lecture. Okay, so we'll go to the browser, go back to our assembler. Source. And paste. Nope, that's the wrong thing to paste. That's okay. We'll go ahead and try again. I think I forgot to do a Control-C to copy. And paste again. And make sure that everything looks good. Alright, so the program is a little bit extended a little bit beyond it. Okay, get rid of that. And that's it. I think we're good here. There we go. And then we get to RAM file. And then we download this to CSV. And we'll call this string length.csv because that's what the program is illustrating. And then we switch to the command line. Okay, it's easier for me to find the command line on my taskbar. There we go. So the only thing we have to change is the name of the CSV. So it's now string length.csv. It runs through. Alright, so we go back to the trace analyzer and analyze our trace. Now, if you have been following me, and looking at the trace analyzer and stuff like that, you can actually make a copy of the trace analyzer when it still has, a result like this. So that way, you actually can keep a copy for yourself. Okay, so we go import. Yeah, doing stuff on the cloud in the cloud, having sharing options and stuff like that really opens up all kinds of possibilities that is just not available when I went to college. There we go. Alright, so we'll wait a little bit. I know we are almost running out of time, but since we don't have to transition and walk all the way to the lab now, it's okay. I can actually use this time too. Alright, it's all done. So let's look for the halt instruction first. The halt instruction can be found using the Assemble tab. And it is supposed to be at location 3.2. So let's look for 3.2. There we go. Alright, so we found location 3.2 in column A, and this should be the last instruction. So sure enough, it is. And we can also see that the program stored 0.3 into location FF. That's the length of the string TAK. So this program also works, and I am going to copy and paste this code as well and post it onto Canvas. So this way you guys also have this sample program in case you want to have a reference of what to do about local variables and what to do about recursion and what to do about dereferencing a local variable. Alright, so I'll go ahead and do that now before I forget. Okay, so Control A, Control C, go back to the other one, paste it here, Control A, Control C again, and then go back to Canvas. So once I paste this one, I'll open up to Knight's lab. And if you guys want to ask questions about that lab, I'll stay online basically, after the lecture, so that if you want to get started with the homework assignment, you can go ahead and ask questions too. So we go to page, new page, and we'll call this string length sample program. There we go. So now you have 2 sample programs plus the one, the one that we did on Tuesday. I did not save or post. But if you go through the video, that one is relatively short, so you can actually just manually copy that one. These 2 are a little bit longer. So this is our lab for tonight. It's function calls. Okay, so hopefully the lab activity will help to reinforce the concepts that I talked about today. And we'll go ahead and check out the passcode to this lab. The passcode of this lab is swap, lowercase swap, and we'll go ahead and set up the due date. So this is the 1st, this is the 2nd, so April 2nd is the date. Alright. Save and publish. There we go. So now you have the lab. I also want to point out that for studying purposes, I'm going to set up a category of ungraded labs, and then I'm going to copy all the labs, at least the ones for this particular exam, to that particular category. So everything under that category has no due date, but the points do not count to your grade either. Basically, you just have the ability to do the lab over and over again for practice purposes, but you can also refer to the instructions of the lab so that if there's any useful instruction in the lab, you have access to that as well. So I'm going to set it up sometime tonight, and if you don't see it after tonight, just give me a nudge. Preferably on Discord, because I check Discord a lot more compared to Exchange now. So if you nudge me on Discord, I'll probably see it right away. And that's it. I think that's the end of today's lecture, unless somebody has a question. I see a few people typing. Okay, just thumbs up. Okay. When is exam 2? Well, that's a very good question. Exam 2 is supposed to be about 2/3 through the semester. So week 11 or so is a good time for exam 2. Next week is our last week before the break. And frankly, at this point, I don't really understand why we even have a break, because we have gone 100% remote, and but we'll still have a break, unfortunately. So I'll go over a practice exam next week, which means after the break, when we come back after the break, we're going to have our exam 2. And again, I got a few people typing, so I'm going to wait. Just because we are home doesn't mean we're not working. Exactly. So we don't need a break. Yes, we still have spring break. Yes, both. I have not heard otherwise, so spring break is still happening, which means I'm not going to lecture during that time, but I'll still answer questions. I'll still check Discord. Spring break quarantine party. It's more like quarantine break party, right? People just break quarantine to have party. We'll see a sharp increase of cases, like 2 weeks after our spring break. Okay, all right. So I think class related stuff is done. So I'm gonna stop the streaming. Oh, so we all webcam ourselves. Well, you guys can do that. Alright, so I'm gonna stop the streaming. You guys can stay on Discord and chat if you want to. So I'm gonna stop the